Time to dive deep into how far our imagination can become reality.
Welcome to Vibe in Action.
Good to see you vibing again.
Vibe in action all the time.
And who's going to vibe along with us today? We have someone new. He's a science communicator, and he's going to make us smarter. Welcome aboard, Dr. Yoon.
Thank you for inviting me for this interesting event. My institution is Korea Institute of Fusion Energy. So this is the only one institute in Korea to deal with fusion energy development.
Wow, what is fusion energy?
So you brought these. These
Yes.
are like
What
your
are these?
mascots. It looks like half the world or planet Earth and half the sun. What does that represent?
It's we call it 억돌이.
Ah,
1억도.
Wow.
100 million in Korean is 1억.
Yeah.
Yes.
Yeah.
It's,
Like in English, it's
yeah.
100 million degrees boy.
Yeah.
That sounds very hot.
Yes, temperature is very important, but it's not the only thing we have to get, but this is kind of must. We have to go to the very high temperature, otherwise we don't have any chance to get the nuclear fusion very active.
So that's the
That's
aim.
why it's very difficult to realize the fusion energy system on us.
Wow.
Before we go into the details, I want to ask you, why do you make such a thing? There's an old saying, there are no two suns in the sky. What's the reason you're making another one on Earth?
I should say many suns doesn't have any issue here. So we have a lot of energy.
More suns, the
But
better?
I think so. Yeah. The main purpose or objective is just for the energy. Because
energy source.
we are running out of energy, right? So for many reasons. I think and I believe that the fusion energy is kind of ultimate or ideal energy source the humankind have developed up to now.
Wow.
So compared with the nuclear power plant, and fossil fuels, there are lots of issues over there, right? So,
Yeah.
But the nuclear fusion is kind of difficult to realize. But in principle, it is much safer and environment friendly and probably cheaper
Oh, really?
than the other sources.
Well, I am truly excited to hear all about the artificial sun he's talking about. But at the same time, I don't know how I'll be able to comprehend and digest everything he's going to talk about today. I feel like we've time traveled to the distant future suddenly.
Yeah, mini sun on Earth, right?
Yeah, can you believe they're making an artificial sun?
Yeah, with that kind of energy as well.
So before we dig deeper, why don't we watch the video first and then continue? Ready? Take a deep breath.
Together.
Vibe
in action.
앞으로 우리가 2050년 이후에는 인류의 미래를 책임져야 될 기술이다.
Well, before watching that video, I thought we were just using our wild creativity and imagining what ifs. What if we built a sun like a superhero, saving the planet, just like the arc reactor in the movie Iron Man?
Yeah.
But now I'm seeing the actual facility and the physical setting, and it is no joke. It is not just a theory. It is happening in the real nonfiction world. And you're saying it is expected to provide nearly limitless clean energy.
Wow.
Well, everyone loves unlimited buffet, so why not?
An energy buffet.
Yeah.
And it's clean
All you
as
can
well.
eat energy buffet.
Yeah, so that would be perfect, especially like these days with AI. They say that that's a power hog, right? I've heard that even some data centers use as much power as a city, right?
That's typical level.
Really? So if we could perfect an artificial sun, surely those kind of worries and concerns would disappear.
Yes, I think it's a promising route. And if we imagine that a lot of energy required for this AI era, And this is really demanding things. And in principle, nuclear fusion can deal with this situation more or less appropriately in many aspects. First of all, we need energy, but we need a very large-scale energy. So AI center is located in a certain region, and then we have to provide high level of the electricity to the center. So we have to be a very large reactor. So fusion reactor is this kind of reactor. So we can make it bigger and very large power plant. So it's good. Similarly, like nuclear fusion reactor.
Yeah.
So because we are using the hydrogen is everywhere.
Yeah.
So we can use hydrogen to fuse themselves to a newer, bigger, heavier element called helium. During this process, we have a lot of heat is coming out. So we are using this heat to generate electricity. So this process is very similar to the other
conventional nuclear power plant.
But the only difference is how we generate the heat. This is different story.
So it's fission versus fusion, right?
Exactly. Yeah.
Seriously, this will put an end to all your worries, especially for me as a Korean. I grew up hearing a lot saying that, Korea is a nation that does not produce a single drop of oil, so you have to conserve energy, turn off the AC, do not waste electricity, and so forth. But we don't have to envy those oil-rich countries anymore.
It's very good attitude, and you have to save energy as much as we can.
Thrift and
Because-
saving have become a habit of mine.
But the main problem, I think, that we always have a shortage of energy, whether you like it or not.
Yeah.
So AI is one thing, and there are lots of needs for the more energy we have to spend.
Yeah.
But there's no pre-launch. So if you really want to get a lot of energy, then we have to be careful. It can be also not so good for the environment for many reasons. When we talk about the nuclear fission reactor, for example, inherently they have a very high level radioactive waste.
Yes.
It can go hundreds and millions of years.
Yeah, it's like the Chernobyl and the
So
Fukushima
it is really
plants.
dangerous, and reactor can be exploding
Yes.
as a kind of disaster.
Oh yeah,
But
we
the
don't want to
nucle-
think about that.
But it happens, right?
Yeah,
So,
yeah. We all remember the disasters.
so luckily, and nuclear fusion does not have this kind of issue, free of it.
Really?
There are some minor event or issues, but we can handle it. But we don't have any severe event like Chernobyl in nuclear fusion. And also, we don't have any carbon dioxide generation.
Oh.
So this is also
That's a
very
good
important
point.
asset for the nuclear fusion.
It sounds like it, yeah. But I can't honestly imagine how we're recreating what's going on in the sun here. You described it briefly with hydrogen and helium, but in terms of what's actually happening and how that's the same on the sun, can you
He made
explain
it
that?
sound like he's making a breakfast toast.
Just 1 + 1 equals a delicious sandwich.
I know
So-
that nuclear power is the primary energy source right
Yes,
now in
exactly.
Korea, but what's the biggest difference from nuclear power?
There are many kinds of nucleus, very light one like hydrogen, and very heavy one like uranium.
Yeah.
So depending on which type of the element we are dealing with, we have a different kind of reactions.
Yeah.
So nuclear fission reactor, they are using uranium,
Yeah.
and they will split this uranium atom or nucleus into two different nucleus.
Yeah.
During this process, we have extra heat generation. That we are using that heat to generate electricity. That's called nuclear fission.
Okay.
So
in
it's
other words, you're
splitting
smashing the atoms.
like just making one element as divided by two.
Splitting them up.
Yeah.
Okay.
One nucleus into two small nuclei.
Exactly. Very nice. And, but the nuclear fusion is the other way around. We are not
You're
dealing
doing
with
it backward.
It's backward, but we are dealing with very light element, not the heavier one. So we are using hydrogen. So hydrogen is everywhere.
Yes.
Maybe two hydrogen merged together as a single nucleus.
You fuse
This
them
is
together.
called fusion. And during this process, also we can generate a lot of heat. So we are using this heat also for the energy production. So there is a different branch, but it depends on what kind of nucleus you are using.
Yeah, the material, the ingredient
Yes,
you
so
use.
I should say that the uranium is not very much in Korea. So we have
We don't
to,
have a
we
lot
have
of
to import.
uranium. Yeah.
But the hydrogen is everywhere. So,
Yeah.
so we can use hydrogen.
Okay, it's not like it's just going to go forever by itself, but we can put in the hydrogen we have.
That's actually violate, physics law. So.
We can't do that.
So it's basically a nuclear fusion reactor, and by the definition of the word fusion, you fuse or you force atomic nuclei together into one big nucleus
Exactly.
by
yeah.
injecting a massive burst of energy.
Yes, we need energy to fuse the nucleus.
In the
That's-
first place.
Yeah, that is my question.
Yeah, so usually the nucleus has charge, so-called electric charge. That is, we call it plus. And the electron. Electron is minus charge. Okay.
N pole and S pole.
That's kind of magnet.
Yeah.
So magnet has also north pole and south pole, and the same pole repel each other,
Yeah.
right? So similarly, for the electric side, there is a positive charge and negative charge. Two positive charge, if you push together, they will repel
Yeah.
very strongly. So we cannot put it to very close distance to fuse. So we have to smash it very hard to go to a very narrow distance. But it is very difficult.
Yeah, you need a big, like a formidable energy to do that.
Yes, the best way to make this kind of condition is you can use a very high speed bullet, for example. So two bullets with very high speed could collide
Oh, wow.
and smash very hardly, right?
Yeah.
So this is the idea. So if we speed up the particle to very high level and collide with these two, then we can make the fusion active. So
And the atoms cannot resist or repel if you add that much speed and
speed,
energy.
yes, exactly. The other way we are talking about this kind of speed is the temperature. So everybody knows the temperature is a kind of measure for hot or cold.
Yeah.
But when you look at the particle level, they are moving very fast. So when you increase the temperature, that means the speed of the element or particle is increasing. So that's why we have to increase the temperature of the plasma, we call it. Then we can make it very high speed particle. Then they can collide and a lot of fusion could occur.
But where do we get that intense amount of energy from?
That's the same question is how we increase the temperature.
Yeah.
You need energy
How
for
we
that as well.
increase the speed and the temperature.
There are several ways. The easiest way is just mixing these low temperature particles with the high temperature particle. Then like mixing the cold water and hot water, then you can increase the temperature of the cold water, right? Very similarly, so we have a very high energy particle injected to the cold plasma. Then we can raise up the temperature of the plasma. So we can reach up to the 100 million degree.
100
Just
million
like
degrees.
this guy.
Yeah.
Wow, he's hot then, isn't he?
It's not that difficult. We have succeeded to generate 100 million degree Celsius even 50 years ago.
Wow.
But
50 years ago.
the main problem is how we sustain it.
The
Bomb.
duration of the temperature.
Yes, it's not a bomb, so we have to sustain it for 24 hours, right? So this is the real problem. So KSTAR is a Korean machine, is working to address that issue. So we are doing a lot of experiment how we can extend the pulse length of the high temperature plasma to certain level. So this is an important task KSTAR is dealing with. So up to now, I think KSTAR has succeeded sustaining this high temperature plasma
For how long?
up to 50 seconds.
Wow.
50 seconds is not a short time.
It's not even a minute.
In normal life,
Yeah.
a minute is nothing, right?
Sure.
But in an atomic level, it is really a long time scale. Usually everything happens in a
Like a millisecond.
millisecond or even shorter. So sustaining in a few hundred seconds,
Yeah.
this is kind of target of KSTAR right now. It's 300 seconds.
Okay.
It's kind of a limit for the successful extension of the plasma to 24 hours. So 300
Like a
seconds after
threshold.
that, yes, exactly. There's nothing hinder the longer sustainment.
Once we get to 300 seconds.
That's why the main target is 300.
But is this only Korea that is doing this? You say KSTAR, so
No,
are we
no.
ahead of the game?
I have to say that Korea is one of the country in a frontier of this kind of research. And the US and UK is also very strong in this field, and also China. Korea is kind of a latecomer in this game.
Wow.
I already told you that it's more than 70 years.
Yeah.
I thought we began early.
No, we don't have enough resources during the time. Actually, we started seriously the nuclear fusion program around 1990s, starting the KSTAR program. KSTAR is first of a kind fusion reactor with a superconducting magnet.
What is a superconducting magnet?
Superconducting means they don't have any resistance. So you can generate a lot of electric current without heat generation. So you can operate it for a long time. We don't have any gravity to mimic sun, right?
Yeah.
On us.
Yeah.
So the other way we can do is using the magnetic field. If you configure the magnetic field in a proper way, like a donut shape,
Yeah, I saw the video. Looks like a donut.
then we can have a very strong magnetic field inside. Then we can lift up the plasma without contact with surrounding materials. 100 million degrees. It's very high temperature.
Yeah, it is even hotter than the sun.
Yes, sun has a lot of gravity, right? So their pressure is immense.
Yeah.
So even a low temperature.
That's how Earth is revolving around sun, because sun has gravity.
Exactly. So you know better than me.
I'm trying
So okay.
as hard as I can.
And the main problem is we cannot reproduce those high pressure conditioning on us. So we use magnet. In magnetic field case, it is typical to use the same reaction as sun. So we are using slightly different one. For that case, we need a higher temperature. That's why we have like 5 or 6 times higher temperature is required, like a threshold temperature for the massive fusion reaction.
Thus 100 million.
As I mentioned before, it is possible, and we already demonstrated to reach those conditions even 50 years ago. So sun is sphere, right?
Yeah.
But it is impossible to use sun's gravity on us. That's why we are using magnetic field. Magnetic field has a different characteristic, like gravity. We have to go to the donut shape, not the sphere, unfortunately. And we call it this donut-shaped machine tokamak.
Tokamak?
It's originated from Russian word, but just meaning like the toroidal device.
Toroidal.
This tokamak will have a plasma inside, high temperature plasma. They will fuse together and generate a lot of heat, and we will use those heat to generate electricity. So this is we call it the basic. Up to now we have a very different kinds of the machine. Tokamak, Stellarate has many different, but tokamak has been the best in the performance. So that's why we are using this tokamak configuration for the main device for the fusion energy development.
Wow.
Bring a top expert's recommendation.
This project is doomed.
I'll write it.
Wow, so the German scientist there must have been like a lifesaver to Korea. So writing a recommendation letter, but if things don't work out, surely there's the risk for the person. So what made him write that recommendation letter?
Well, more than anything, I'm shocked that Wagner is not a composer. He's a German scientist.
Yeah, they can be scientists as well.
So Professor Wagner is a very brilliant physicist,
Yeah.
and he supported KSTAR program.
Wow.
Because at that time, KSTAR program is very advanced and kind of high risk. but we managed it anyway. So there was some issue for the design and the target of the KSTAR. So a lot of people in the world did not believe it will work or success. And
They
in
had
that
doubts.
regard, Professor Wagner actually support us quite well. Partly due to the Korean industry has a lot of things, shipbuildings and very accurate manufacture processings.
Yeah.
And also based on us because of our advanced industry development.
Okay.
Because we need very accurate manufacturing
Yeah.
of the machine, otherwise we cannot get the performance. So we have a very good car company, for example.
Of course,
So-
yes.
and also the shipbuilding, and we have a large scale structural mechanics. That's why he thought those kinds of merit we have will make it possible. KSTAR can be built in Korea without a big problem.
So he sort of wrote us a letter of recommendation when we were desperate to go to college. Thank you, Professor Wagner. Danke schön. And it is thanks to him that we were able to build a superconducting tokamak back in the 1990s when we didn't even have an experience of building a regular tokamak, right?
I think it was critical, thanks to him. So because he wrote a very good letter to Korean government, for example, then so it is great help to proceed at that time.
So fast forward to 2026, is the world now in a kind of every country for itself race to secure the most advanced artificial sun?
There is partly true, but there are different approach. So I have to talk about the international project called ITER. ITER is way in Latin, right? So new way, something like that. So ITER is a very big machine. It's much, much bigger than KSTAR. And it's aiming at demonstrating the real fusion power generation, first time ever. It was under construction in southern Provence, in France,
Yeah.
near Marseille. So we are getting the first experiment around 2034. Then we can see a lot of power is coming out from that machine. So this is very big machine and very expensive actually. So more than 20 billion US dollars. Expensive ever, project.
Just full
in
stop.
the, in, the,
Undertaken.
in the human history.
Wow, the biggest construction
because
project ever.
it is worthwhile, right? So it's to demonstrate the fusion energy development. Korea is one of them. So all of the 7 advanced country, EU,
US,
Japan, China, Russia, India, Korea.
Oh, wow. That's a
7 member
select group.
countries.
Yeah.
So this is an international collaboration.
Sure.
It's not like a dog eat dog kind of competition.
We are building ITER together. So interestingly, the ITER project is based on the procurement base. That means that each country has to provide certain subsystems.
Like a potluck party.
Yes, exactly. The magnet probably comes from Japan, and the vacuum vessel may come from Korea. We are providing all the subsystem, then we will assemble those systems on site.
In Marseille.
Yes, near Marseille.
It is so cool to see such a joint effort. It's a true international cooperation.
Yes.
Yeah.
Because energy is such an imminent issue.
For the globe, right?
Yeah.
Yes, so we are working together, and unfortunately, up to now, we have many issues still remain to be solved. So,
For example,
I mentioned the magnet. So we need a very strong superconducting magnet. So it is really demanding, and up to now, we are not 100% successful to get the final one, but we are quite close. So we are working together to build a large-scale superconducting magnet with advanced technology. This kind of example, so we are working together. Because ITER is too big, it's also very expensive, so we are sharing the financial load also.
are
So-
we financially contributing to the project as well?
Yeah, as I mentioned, this is kind of both. We are providing some financial support on site and also for the providing the
Equipment.
subsystem. So it's going both ways.
But one concern might be, you know, Korea, we've put a lot of work into things like KSTAR and these components, then we send them off. What if other countries benefit, or what if France just says, we're going to keep this ITER now, it's on our land?
Thanks for asking on behalf of all Koreans.
Korea also providing some technical backgrounds. The US and UK has been working for 70 years and a lot of experience there. And they are sharing this valuable experience. So I think we are working actually really together. So not a single country can deal with this large project properly.
Scientists are like putting their heads together regardless of their national interest.
Coming together.
It's not for the commercial things, but just demonstrate the physics and the realization of fusion energy, whether it's really working or not.
Well, this is a silly question, but how will you divide the outcome? Let's say if we succeed in achieving the goal of reproducing the sun's enormous energy, and the Nobel Committee decides to give us an award. Who gets the award?
We call it intellectual property issue.
Yeah.
So how we share all the patent
The
and
rewards.
something like. Interestingly, ITER project is IP is equal to every member country. So we are sharing all the IP together. So we can build Korean reactor based on ITER without issue, and UK also. This is really a collaborative work.
Yeah.
But this is not the only way we are moving. As I mentioned, ITER is very big and very expensive, and it takes longer time to build. Thanks to the recent development of the magnet technology, there is a chance to get the smaller machine.
Oh.
That's why Korea is also aiming at the building another one, means that this smaller machine locally in Korea. Other countries have a similar plan. So in that case, every country can do the job by their own capability. So there is international collaboration
Yeah.
centered by ITER project, and also that there are some international competitions.
Yeah.
Who will be the first to build a machine?
A smaller scale.
Yeah, smaller scale.
So the main gigantic, humongous ITER machine will serve as a benchmark for other member countries to follow through.
Yes, you are quite good at understanding what
Thank you, sir.
ITER is baseline technology.
Yeah.
And based on that, we can build smaller machines in each nation.
Only we can come up with an alternative sun. There is nothing I would ask for. It is no comparison to who's developing a faster GPU or CPU. It is an energy problem.
Yeah. It's a root thing that we need to solve, right?
So now that we've covered pretty much everything from the principles of an artificial sun to its current development process, shall we take a moment to cool it down a little bit?
Yes.
Time to recap what we've learned so far.
Yes, please.
What is the artificial sun being built on Earth?
A project to recreate the sun's energy on Earth through nuclear fusion.
A next-generation power technology that generates massive energy by fusing hydrogen.
Capable of producing electricity without carbon emissions. Fuel comes from hydrogen in seawater, an almost limitless energy source.
Once the artificial sun is complete, an era free from energy worries will arrive.
Oh, that's great to see everything that we discussed laid out again. My head was overheating a little bit, yeah.
It's clearly a bright, sunny day for us.
Yes.
But understanding an artificial sun and actually seeing it on site must feel completely different, right?
Yeah, I assume so. And to stay ahead with this nuclear fusion ecosystem, surely research is ongoing and new discoveries are being made all the time.
I want to see the artificial sun shining, but I left my shades in the car.
Yeah, we'll need more than regular shades as well, right?
To see is to believe, right?
Yeah.
So it's really good for you guys to visit KSTAR and even ITER in your future.
ITER in France.
That'd be amazing.
So when you look at the size of the machine, it's really huge. So you
How
can-
big in comparison to buildings?
Total yard
Yeah.
of the ITER site is 10 soccer play
10
10
times bigger?
times.
The square footage?
Oh my
And
goodness.
the main machine is also very big. It's really difficult to explain to you guys. And the best way is to look by yourself. I think it's the biggest structure humankind ever made,
Wow.
In terms of for scientific research?
including everything, I
Oh,
think.
what, including like the
Yeah.
Burj Khalifa, like the tallest building in the world or something?
Maybe smaller than pyramid, but
Really?
Oh, wow.
I
smaller
thought
than
it was like
pyramid.
a 5-story building high.
No. The machine itself like 30-meter high, and even the building itself is very high.
Oh, wow.
The basement also is quite deep.
Wow, and do French people living nearby know that it exists right in their neighborhood?
Sure.
Free energy they're looking forward
And
to.
No danger involved, right?
I'm still afraid there's no pre-launch, right? So if you have a lot of energy, that means we have some issues. But question is whether it is manageable or not. We're gonna build smaller ones. On a size scale, it's like 1/3 of the ITER.
Oh, that is still
but still
pretty large.
have a similar power.
Here in Korea.
Yes, and also there are some other plans in the world. In Korean case, I think we can finish up the construction by the 2030s and start to generate electricity. Wow. And luckily, the Korean government supported very strongly. So you may heard about the K-Moonshot project, recently launched
K-Moonshot?
by the Korean government, the national agenda for the scientific program, to which area will focus in 5 or 10 years. So fusion is one of them. So we have a strong support. I hope we can make it in time. And for that, in KOP, Korean Institute of Fusion Energy, we have like 200 scientists and engineers and working together.
Wow, I had no idea we were growing so many suns right near us. Wow. We're gonna take you to hands down the hottest place on Earth. Shall we go see what's happening at the Korea Institute of Fusion Energy? Let's do it one more time. 5 in action.
Where researchers are working to recreate the nuclear fusion reactions that occur at the core of the sun here on Earth. This is the Korea Institute of Fusion Energy. KSTAR, known as Korea's artificial sun, is an experimental device that verifies core technologies for future nuclear fusion power plants. At the heart of nuclear fusion is plasma.
융합 에너지라는 거는 기본적으로 수소와 같이 가벼운 핵을 서로 합쳐서 다른 핵으로 만들면서 거기서 에너지를 얻어내는 건데요. 핵을 서로 합치기 위해서는 이 핵에 있는 전자를 먼저 떼어내야 됩니다. 이렇게 핵과 전자가 분리된 상태를 플라즈마라고 하고, 이 플라즈마를 1억 도라는 높은 온도까지 올려야 비로소 핵융합 반응이 시작될 수 있기 때문에 이제 플라즈마가 중요하다 이렇게 말씀드릴 수 있을 것 같습니다.
The challenge is that plasma is extremely unstable. To become a viable power plant, it must be confined within powerful magnetic fields and operated continuously for hundreds of seconds or more. In experiments conducted at the end of 2024, the Korea Institute of Fusion Energy successfully maintained 100 million degree plasma for 48 seconds, setting a new world record. This marks another major milestone on the path toward commercial nuclear fusion.
저희가 파이어 모드라고 부르는 운전 모드를 개발했는데 이걸 가지고 네이처에도 출판을 하고 다 성과를 이뤘고요. 2022년부터 계속 연구를 하면서 1억 도 플라즈마 기록을 계속 갱신하다가 2024년도에 48초라는 최장 기록을 달성을 했고요. 이 기록이 지금까지도 깨지지 않고 있는 그런 기록입니다. 1억 도라는 온도를 충분히 만들 수 있다. 그리고 이거를 길게 유지할 수 있다는 것을 보여주는 의미가 있고요. 그렇게 되면은 이 핵융합이라는 게 단순히 우리가 상상만 하던 그런 에너지가 아니고 실제로 만들 수 있는 에너지라는 이제 믿음을 가질 수가 있게 되겠죠.
As efforts to address the climate crisis and accelerate the energy transition intensify, countries around the world are moving beyond experiments and preparing to generate electricity from fusion. KSTAR is also accelerating the validation of technologies needed to operate future demonstration fusion reactors. One of the biggest changes is the material used inside the reactor. Researchers replaced the divertor, a critical component that directly withstands the plasma's heat, from carbon to tungsten. With a melting point of over 3,400 degrees Celsius, tungsten is expected to play a crucial role in commercial fusion power plants. However, if tiny tungsten particles enter the plasma, the reaction can become unstable in an instant. The researchers' solution is AI. Hundreds of sensors continuously monitor the plasma in real time, while AI detects early signs of instability and immediately adjusts magnetic fields and heating power. In moments when human operators cannot react quickly enough, AI steps in first.
실증로에서는 이 안정성과 경제성이라는 두 가지를 다 잡아야 됩니다. 그렇게 하려면은 굉장히 좁은 영역에서 제어를 해야 돼요. 우리가 이제 뭐 계산을 한다거나 이제 머릿속으로 생각을 해서 찾기에는 굉장히 어려운 측면이 있어요. 이 AI를 활용하면은 플라즈마의 굉장히 미세한 변화를 빠르게 캐치를 해서 운전 경로를 잘 따라서 운전을 할 수 있도록 만들 수 있겠다, 이런 기대를 하고 있습니다.
The next goal of all these experiments is to develop the operating scenarios needed for a fusion demonstration reactor. The target is to achieve this by 2030. To realize fusion energy as early as possible, the testing period at the demonstration reactor stage must be shortened. The government is also stepping up its efforts. This year, the nuclear fusion research budget has nearly doubled from the previous year to approximately $75 million. The goal is to build a Korean fusion demonstration reactor in the 2030s and move toward generating electricity from fusion power.
저희가 준비하고 있는 게 이제 가상핵융합로가 있어요. 가상으로 케이스타를 만들어서 이 케이스타가 실제로 돌아가는 것과 똑같은 걸 한번 모사를 해보겠다, 그런 목표로 지금 굉장히 많이 진전이 되어 있고요. 이 가상핵융합로는 쉽게 그 실제 실증로 사이즈로 늘려가지고 다시 돌려볼 수가 있잖아요. 케이스타와 가상핵융합로 기술 그리고 AI 기술을 결합해서 실증로 시나리오를 예측하고 개발을 해보겠다, 이런 목표를 가지고 있습니다.
When nuclear fusion begins generating electricity, how will the energy landscape change?
핵융합 발전소라는 게 굉장히 좋은 특성이 많이 있거든요. 대표적으로 이제 뭐 건설하는데 입지 같은 제약을 많이 안 받는다는 게 특징이 있고, 뭐 도시 옆에도 지을 수 있고, 뭐 데이터 센터 옆에도 바로 지을 수 있고, 그리고 또 24시간 꾸준하게 기저전력을 생산할 수 있는 그런 장치라는 장점이 있어요. 만약에 핵융합이라는 거를 기존의 어떤 다른 수단의 단가와 비슷한 수준으로 맞추는 단계에 온다면은 기저전력 분야에 있어서는 핵융합이 굉장히 많은 부분을 대체를 할 수 있지 않을까 생각이 듭니다.
From experimentation to demonstration, Korea's artificial sun is now moving toward a future that generates electricity.
As I was listening, if I'm honest, I was thinking, yeah, this is incredible, but is it really going to happen? But after seeing it, as you mentioned, seeing is believing, it does genuinely feel hopeful, like this is going to be possible. A reality 2030s? That's not too far away.
Yeah,
Unbelievable.
ditto. Yeah, we've just seen the research center up and running. And I've seen Mr. Yoon.
In the flesh.
There is still a long way, I believe. Fusion system development takes a lot of time and resources. So we have to go in a long step rather than short one. So 2030, in 15 years, we have to demonstrate everything. So this is quite demanding. We need the technology development to build this machine in parallel with machine design and construction. So for that purpose, we are building a new infrastructure to deal with technology development. Southern part of the Korea, Jeollanam-do, Naju City. We're going to build a new complex of all the technology center.
But at the same time, maybe some of our viewers might have concerns like, is this artificial energy actually safe? Because it's not natural, it is man-made, artificial. And you've already mentioned that it is inherently impossible to produce radioactive waste because it does not create chain reaction, in contrast to nuclear fission. But tell me again, if this is really safe, and what happens when nuclear reactions are not controlled properly.
There are some concerns over there, right? I understand. And I can resist to say that nuclear fusion is most safe and environmental friendly and also cheap. So the reason why I'm trying to argue with this aspect is we are dealing with very light elements. So light elements do not have any radioactive characteristic. So uranium is a very heavy one, and they are decomposed to two different elements, then they are radioactive. But we are fusing the light elements, so we don't have any high level radioactive waste. This is a real merit or advantage of nuclear fusion compared with nuclear fission. And the other part is we don't have any carbon emission.
At all.
This is also important. Of course, during the construction, we are using steels and we have some carbons, but the operation itself doesn't produce any carbon dioxide. So I believe this is a very strong advantage. And for the operation. So I'm not sure it is the advantage or disadvantage of the machines, but we can shut down the fusion reactor very quickly.
Like an on-off switch.
Yes, when you turn off the switch, press the button, then it goes to the zero.
Oh, wow.
Because it's a kind of a subcritical system. There shouldn't be any big explosion or heavy disaster and a lot of things are coming up and explode. There's nothing like that.
I'm so relieved.
That's inherently safe in the operation. The other way around, I should say, so it is difficult to sustain it.
To keep it going.
So this is the issue. We have different problem. We're going to solve this problem anyway with the ITER and the new machines and also from KSTAR. So I think it's not a big problem. We are moving very fast to extend the pulse length right now.
So reassuring.
Yeah.
Well, then I guess all the doubts have been cleared and all possibilities have been explored. So until the day an artificial sun rises here in Korea, either in the west or in the east, we'll be cheering on the journey of KSTAR every step of the way. Thank you so much for watching till the end. And everybody together.
One last time.
Vibe in action.
Wow.
Today we're going to talk about a truly transformative technology that is called green hydrogen.
Hydrogen has color?
The most eco-friendly because we only require water. Maybe we could power ships, planes, spacecraft with hydrogen in the future.
Let's live long so that we can see all these technologies unfold before we die.
I hope so, yes.